Welcome to this video lecture. In this lecture, we will discuss how to digitize an analog signal through its sampling and quantization. When sampling a certain signal, the sampling rate must be set such that the analog signal can be reconstructed from the available discrete samples with minimal loss of information or with sufficient accuracy. This sampling theorem sets the basis for modern digital communication systems and for other branches of signal processing. So let's start the lecture with discussion on the sampling theorem. To prove the sampling theorem, let's consider a B-Hertz band limited signal g of t in time domain, while its frequency domain representation after taking the Fourier transform is g of omega, where the signal is defined as bandwidth B-Hertz limited. So it occupies a band from 0 to B-Hertz, that is 2 pi b radians. While if we see the frequency axis in terms of f, that is in terms of hertz, then this signal has a bandwidth b hertz, and this is a baseband signal which lies in the base of frequency spectrum. So in time domain, this signal is continuously defined along all time instances, while in amplitude axis, this signal is not restricted to any finite number of amplitude levels. So such a signal can be referred as an analog signal because it is not restricted to a finite set of amplitude levels, and this signal can be referred as a continuous signal along time because its definition is available along time at all time instances. So if we want to sample this signal and want to select a finite number of its samples, then that can be accomplished by multiplying this signal g of t by an impulse train, for example, a signal which consists of multiple unit impulses repeating periodically after every ts seconds. So such an impulse train signal can be plotted in time domain as, and if we refer this train of impulses, this signal as delta with subscript capital Ts, and this is a function of time. So we have impulses defined along time which are repeating periodically after every Ts seconds. So the separation span between each of these impulses is, for example, Ts seconds. So after multiplying the signal g of t that is plotted in figure A with the signal that is plotted in figure B, which is a train of impulses, we can obtain the sampled version of signal g of t, which we can refer with, for example, g bar of t. This sampled signal consists of impulses spaced every ts seconds, which are scaled according to the amplitudes of this given analog and continuous signal g of t. So after multiplying these two signals, we can obtain a signal, for example, as plotted in figure C. So if G is the continuous signal which we are sampling, then we can refer this sampled signal as G bar of t. And in this sampled signal, we have impulses which are spaced every ts seconds. This means that the nth sample is located at time instant n into ts, where n is the index of the sample and ts represents time interval of each sample. So by this we can calculate the time of every sample where index of the sample is available. And for that subject time instant, for example t, the strength or the amplitude of the given analog and continuous signal g of t can be represented by g of t, which is for every given index of the sample we can calculate its amplitude as g of nts. That is, n represents the index of the sample and ts represents the span of every impulse. That is, we can obtain g bar of t by multiplying g of t with a train of impulses that we have referred here by delta with subscript ts as a function of time t. As this impulse train signal is a periodic signal of period ts, as it is repeating after every ts seconds, it can be expressed as a Fourier series. So as we have already seen an example in chapter number 2, the trigonometric Fourier series expansion of such an impulse train signal can be represented by an impulse train signal in frequency domain, while the separation span between two adjacent impulses in this frequency domain representation will be inversely proportional to the separation span that was between the two adjacent impulses in time domain. So this separation span is equal to 1 over Ts, while Ts was the separation span between two adjacent impulses in time domain. So, Fourier series expansion of an impulse train signal can be obtained as an impulse signal in frequency domain, while the separation span between the impulse train signal in time and frequency domains is inversely proportional to each other. That is, if we represent this separation span of two adjacent impulses in the impulse train signal of frequency domain with Fs, which will be equal to 1 over Ts, then by increasing the separation span between two adjacent impulses in time domain, we will observe a reduction in the separation span between two adjacent impulses in frequency domain as its equivalent operation. So as we have obtained this sampled signal by multiplying the given continuous signal with a train of impulses, therefore the equivalent operation in frequency domain can be represented as convolution of the given continuous signal with the impulse train signal, which we, for example, if we refer the impulse train signal in frequency domain as capital delta of omega or capital delta of f. So in frequency domain we can obtain representation of this sampled signal g bar of t by convolving the given continuous signal, that was g of omega, with the Fourier transform of that impulse train signal, which is delta of f, for example. That is, we will receive a copy of this given continuous signal's frequency domain representation at the position of each impulse in delta of f function. That is, an impulse located at 0, and there was an impulse located separated from 0 with fs Hz frequency, and separation between each of these impulses was set as fs Hz. So another copy of the given continuous signal will be received at 2fs, another copy of this same given signal will be received at 3fs, and so on, and their mirrored images will be seen at the negative frequencies. That is a copy of the given continuous signal at minus fs Hz, and a copy at minus 2 fs Hz, and a copy at minus 3 fs Hz, and so on. So we have an original copy centered at 0 frequency, while its images can be seen separated from it at fs Hz and 2 fs Hz and 3 fs Hz, and so on. So this signal represents the spectrum of sampled signal g bar of t, which can be labeled as g bar of omega. So from this frequency domain representation of the sampled signal, that is g bar of omega, an important conclusion can be drawn. That is, if we are to reconstruct the original continuous signal, that is g of omega, from this sampled signal, then we must avoid any overlapping between these consecutive representations of the given g of omega signal. That is, as the bandwidth of this given g of omega signal is b Hz, so the representation of this part of the signal is b Hz, and the representation of this part of signal is also b Hz. So to avoid overlapping of these adjacent representations of the same signal from each other, the separation between the central position of these spectrums must be at least 2 bHz. Any separation less than 2 bHz will cause overlapping between the tails of these adjacent representations of the same signal g of omega. That will restrict us from reconstructing the original g of omega signal from this g bar of omega, the sampled signal. So there must be no overlap between the successive representations of g of omega in g bar of omega. These two adjacent representations of g of omega must not overlap with each other in order to enable us to reconstruct the original signal g of omega from this signal by passing it through any filter in frequency domain to retain its one copy, the baseband variant, while filtering all of its other copies. This reconstruction will only be possible if and only if there is no overlap between the successive representations of g of omega in this sampled signal g bar of omega. That is, to ensure no overlap, as the band of g of omega is b Hz, this no overlapping can only be ensured if the frequency fs is set as at least 2 bHz. So we can draw this conclusion from this graphical representation that fs must be equal to or greater than 2 bHz. where B was the bandwidth of the given continuous signal g of t. As we are aware that Ts, the separation span between two consecutive impulses in the sampled signal, is equal to 1 over Fs. Therefore, we can draw this conclusion that Ts must be equal to 1 over 2b, where b is the bandwidth of given continuous signal. As the signal under consideration here is a baseband signal, its maximum frequency represents its bandwidth, so we can rephrase it as the sampling frequency must be twice the highest frequency of the signal which is being sampled. So let's re-evaluate this analysis mathematically. The signal which was plotted in figure B was a train of impulses which we represented as delta with subscript capital T S, and it was a function of time. It has multiple delta functions, multiple impulses which are separated from each other with Ts seconds, while the index of each impulse is small n, and by adding up all of these impulses we can obtain the representation for this impulse train signal in time domain. In order to obtain the sampled signal which was represented by g bar of t, we multiplied the given continuous signal g of t with this impulse train signal, that was delta ts. So by substituting this equation number 1 in equation number 2, we can obtain a time domain expression for the sampled signal g bar of t, which is equal to, that is choosing the samples of g of t after every ts seconds, while n here represents the index of these chosen discrete samples. As we have discussed that the impulse train signal is a periodic signal of period Ts, it can be expressed through Fourier series expansion. The trigonometric Fourier series expansion of this signal is also an impulse train signal, while the separation span between two consecutive impulses in time and frequency domain impulse train signals is inversely proportional to each other. And we are also aware of the fact that a sinusoid in time domain can be represented with an impulse in frequency domain. So each of these impulses in frequency domain can be written by pure sinusoid signals in time domain. Through this observation, we can obtain another representation of this impulse train signal in time domain. That is, we have multiple impulses in frequency domain, while each of these impulses can be represented as a sinusoid signal in time domain, where the frequency of the sinusoid representing a certain impulse in frequency domain will be the frequency where that impulse is positioned. For example, the impulse positioned at zero frequency can be represented by a constant number, while the impulse positioned at frequency fs, for example, can be represented by a sinusoid, for example 2 pi fs t. Plus, the impulse positioned at, for example, 2fs will be represented by another sinusoid with frequency of 2fs. And so on, the impulse positioned at frequency 3fs will be represented by a sinusoid where the frequency of the sinusoid will be equal to 3fs. Precisely in the trigonometric Fourier series expansion, the scaling factor of the sinusoids was 1 over ts, where ts was the separation span between two adjacent impulses in time domain. And this sampling frequency fs is equal to inverse of the separation span of two adjacent impulses ts. And if we substitute this expression, for example expression 3, in expression 2, we can obtain another representation of the sampled signal in time domain. For example, g bar of t can be represented as, that is g of t being multiplied by this impulse train signal equals to, by substituting equation 3 in equation 2 here, 1 over ts, g of t multiplied by 1 will be equal to g of t plus 2 g of t into cos of omega st, where omega s is equal to 2 pi fs, plus 2 g of t into cos of 2 omega st plus 2 g of t into cos of 3 omega st, and so on. So from this expression we can observe that the first part is the pure continuous given signal g of t in its original form. Therefore its Fourier domain representation will be its original representation, that was baseband signal positioned at 0 Hz and band limited to b Hz bandwidth. While Observing this additive second part in this expression, we have a constant number 2 which is a scaling factor, while the given continuous signal g of t is being multiplied by a sinusoid signal. Multiplication of any signal with sinusoid in time domain represents its shifting in frequency domain, which, if you recall, we have also exploited this property of Fourier transform for designing amplitude modulation schemes. So by multiplying this g of t signal with a sinusoid will represent frequency shifting of g of t signal from its original representation to omega s units apart. That is a shift of omega s units. So from this second additive representation, we obtain a spectrum of the given g of t signal shifted in frequency domain by fs units. So its mirrored image can also be observed, that is at minus fs. Similarly, the third additive term also has g of t shifted across 2 omega s. So the same spectrum g of omega shifted across 2 times of omega s or 2 times of fs, and so on. We have a copy of g of t shifted across 3 times of fs, and we will have another copy here at 4 times of fs and another copy at 5 times of fs, and so on. So we will have successive copies of the original given signal g of omega in the sampled signal g bar of omega. So the spectrum which we plotted for the sampled signal can also be authenticated by this time domain expression, which we obtained through trigonometric Fourier series expansion of the impulse train signal of time domain. So as we have multiple representations of g of omega in g bar of omega, we can write an expression for g bar of omega as where g of omega shifted at 0 frequency is available, and another copy of this g of omega shifted at omega s is available, and another copy shifted at 2 omega s is available, and so on. By substituting an appropriate value for n, we can represent one of the copies from this spectrum, and by adding all of these representations together along n, we can write an expression for this sampled signal's spectrum, that is g bar of omega. So as discussed earlier, we can observe that we have the original spectrum of g of omega positioned at 0 frequency by substituting 0 as the value of n here, and we have another representation of the same signal g of omega that is shifted by omega s units in frequency domain, for example omega. That is, by substituting n is equal to 1 in this expression, we can obtain this copy. Similarly, by substituting n is equal to 2 in this expression, we have another copy of the original given signal that was a continuous signal in time domain at 2 times of omega s. Similarly, another copy will be available at 3 times of omega s if we substitute n is equal to 3 here, and so on. So if we want to reconstruct the original signal that was g of omega from this sampled signal g bar of omega, we can filter it through a low pass filter that will pass the low frequency components, and it will stop all the band which is composed of higher frequencies. By passing it through a low pass filter, we can obtain g of omega from g bar of omega. So to reconstruct the original continuous signal from this sampled signal, we can use a low pass filter. While to ensure that the original signal g of omega is accurately reconstructed from g bar of omega, we need to avoid any overlapping between the successive representations of g of omega, as we are aware that the spectrum of g of omega occupies a band of 2 pi b in terms of radians per second. So to avoid the overlap between two adjacent copies of this given continuous signal g of omega, the sampling frequency omega s must be set as 2 times of 2 pi b. That is, fs should be set as greater than or equal to 2b, that is, ts should be set as less than or equal to 1 over 2b. If this condition is satisfied, which can be represented in terms of radians per seconds or hertz or in terms of seconds in time, then a low pass filter can be used to reconstruct the original continuous signal g of omega from the sampled signal g bar of omega. While in this reconstruction example, we have considered an ideal low pass filter which ideally passes one copy of this g of omega's representation in g bar of omega and stops all the other copies of the signal which are at higher frequencies. So this definition is the definition, which is referred as Nyquist rate or Nyquist interval, or this theorem can be referred as Nyquist sampling theorem. The process of reconstructing a continuous time signal g of t from its discrete samples is also known as interpolation. That is, a band limited signal g of t can be reconstructed from the sampled signal g bar of t by passing it through an ideal low pass filter. So this interpolation process here can be represented through ideal low pass filtering in frequency domain. While we will thoroughly examine this process of interpolation with different viewpoints in our following lecture, where we will also discuss different implications which can occur when reconstructing the continuous original signal from its discrete samples. We have just briefly discussed this interpolation operation in frequency domain, while in our following lecture we will thoroughly discuss it in both time and frequency domains, and will also discuss any associated implications with it. Thank you for attending this lecture. I hope you gained a good understanding of the topic. If you have any question, you can write it to me through email, or you can ask it during our upcoming online session. Thank you.